Yes, hello and welcome to CoqPL. We're happy to see you all. Please feel free to also use the seats, which are a little bit more up front, because like poor Armaël will be very lonely here, and I don't think we will get to the full 500 people in this room. Can't hear you? Okay, perfect. Yeah, it's too far. So yes, welcome to CoqPL. Just for those who want to know, because that's mostly like one of the most popular sessions, the session on the Coq development team will actually be today the second session and not as traditionally the last session, because Mathieu, who has kindly agreed to give this session, will be on a train already at this time. So just for everybody who wants to join the session, this will already be at 11 at the first session. Okay, and otherwise, I will give the stage to our invited speaker, Armaël, who will talk about Melocoton.
Thank you very much. So yeah, this is Melocoton. This is joint work with all these cool people. Johannes and Simon are at Popel, if you want to talk to them, as well as Lars and Derek. All right, let's get started. So in this work, we are interested in so-called multi-language programs. And these multi-language programs are maybe a bit more common than you might think. A few examples include NumPy, a Python library for fast number crunching, implemented in Python but with routine in C and Fortran. Firefox includes code in C++, Rust, and JavaScript. Another example is OpenSSL, which is itself a pure C library, but is very useful, so ends up being included in other programming languages with bindings for Rust, Python, OCaml, Go, and so on. So in particular, I was interested in interoperability between OCaml and C programs. And sure enough, if you look on OPAM, you can see that there are some bindings for OpenSSL in OCaml. And if you look at the code, you can see that these are implemented using a mix of OCaml and C code. And the C code does not include the OpenSSL code. It is just a wrapper code that is used to expose the C library as a normal OCaml library that you can use from standard OCaml code. And the way this works is that this wrapper code is going to use the OCaml foreign function interface, or FFI, which is a set of primitives that you can use to write this kind of code. And wrapper code has actually quite a tough work to do, right? Because now it has to bridge between these two very different languages, OCaml and C, where OCaml is a high-level functional language with purely functional data structures, structured values, and so on, and automated memory management with a garbage collector. And on the other hand, C is lower level, has pointers to manipulate memory, and manual memory management. We also want typically the wrapper code to be efficient and not introduce unnecessary overhead. So this is kind of a pick 2 out of 3 situation, and as a result, OCaml FFI code is typically very unsafe, and it has to follow many subtle rules dictated by the FFI. And if you fail to follow these rules while writing the code, then you might segfault your program, corrupt its memory, or just break the type safety and data abstraction properties of OCaml. So the question for us was, well, how can we verify the correctness and say functional correctness of this kind of code written in different languages with different memory models? If we look at the existing work for verification of functional correctness of single languages, there is a lot of existing work. This is just a sample of papers from our field in the last few years. And if you go and read them all, you can see that there is a sort of recipe that works very well, which is to equip your programming language with a program logic. Maybe you will use whole logic for a simple imperative language, or maybe you need some more modularity or reasoning about aliasing, and you will use a separation logic. But that works fairly well. Now, if we look at the picture for in the multi-language setting, the picture is a bit more sparse. There is some existing work on semantics, in particular in the CompCert setting, and logical relations with Ahmed's work. But here we are really interested in proving the correctness of specific programs that combine these unsafe languages and with the unsafe FFI, but we'd like to be able to prove that for a specific program, this program actually follows the rules and is safe. So this is what we set out to do. And to my knowledge, Melocoton is the first program logic that can deal with these multiple languages with very different memory models. All right. So let's look at a concrete example of this kind of program mixing OCaml and C. And for the sake of the example, we'll say that we'll assume that we have this C function hash pointer, which takes a pointer to an integer and hashes it, replacing the integer in place. And let's say that this function uses state-of-the-art cryptography, and I don't know, like is very complicated, so we want to reuse it off the shelf and not port it to OCaml or something like that. And we want to use it from an OCaml program that does other stuff. So here, for the example, it's going to be a simple program that creates a reference containing an integer, calls some hashref function, which is supposed to go in the reference and hash the integer inside, and then print the content of the reference. And the idea here is that hashref is going to do the same as hash pointer, but on the OCaml reference, by calling under the hood the hash pointer C function. So these two parts don't really connect yet. So what we need to do is to write some what we call glue code, which is going to be implemented in C here, with this extra camel hashref function. And this is going to be a C function, but a C function that receives as an argument and produces as a result OCaml values of this value type in C here. And then the idea is that camel hashref is going to use these operations of the OCaml FFI written in yellow to first read into the contents of the OCaml reference, turn that into some C stuff that it can pass to hash pointer, and then read the hashed integer and write it to the OCaml reference, and finally return unit. All right, and the idea is that overall this function is going to behave just like an OCaml function. And finally, we need to do a last bit of stitching, which is to indicate to the OCaml compiler that whenever we call hashref in OCaml code, then we actually need to just call the camel hashref C function. And this is what we do with this external definition. And we also need to just give an OCaml type for this function, which the OCaml compiler is just going to trust. All right, so this is the complete example for this talk. And as you might guess, the tricky part is the bottom part. It's the part with the glue code. And why? It's because all of the use of this operation is not statically checked. There are many mistakes that we could make, either by misusing the functions of the FFI on the right. Maybe we do some small overflow and read or write outside the block, or we fail to respect some of the other invariants of the FFI. Or maybe we write a wrong type annotation on the left. Either way, if we do any of these mistakes, it's not going to be caught by the compiler. The program is going to run and it's going to explode at runtime. So what we wish to do is to design a program logic that gives us reasoning rules, pre and post conditions for all of the operations that appear here, so that overall we can statically check those and prove a specification for the overall code that ensures that we have steered away from all the possible mistakes. Very good. And of course, I'm here talking at CoqPL, so I want to do all of this, but also foundationally in Coq, so that I can slap a big verified in Coq badge on top of this. All right. And I have good news, which is that we have a tool to do all of that. It's called Iris. Iris is an expressive separation logic framework implemented in Coq to build custom program logics. Excellent. And to do that, the Iris provides us with a methodology where there are roughly 3 steps. The first is to define some operational semantics for your custom language in Coq. Then you have to define how to interpret the state of a program as a separation logic assertion in Iris to give modular reasoning principle about your state. And then you go through the operations, the primitive operations of your language, and you prove reasoning rules for each of them against this interpretation. Excellent. So it seems we might actually have a simple solution to our problem, right? There seems to be a clear path ahead. Why don't we just, apply the ARIS methodology to this big OCaml plus C plus FFI language that we seem to have going on? And it might work, but then I'll let you think for a second of defining just the inductive type for the syntax and semantics of OCaml plus C plus FFI in Coq at once. And you might start to think like me that this is going to be unpleasant and unsatisfactory, both for engineering and conceptual reasons. And indeed, if we look at like most multi-language programs, they look like this. A big part of the problem is just business logic, either in, say, OCaml or C, that is normal single language code. It's completely oblivious to the other language on the other side, and it is normal code. And then a tiny part of the code, which is the glue code, is where all the tricky language interaction actually occurs. So there is a lot more structure here than an arbitrary intermixing of the 2 or 3 languages. And so we believe to build the formal account of that, we also want to have some extra structure. And what we say is that we want to follow this extra design principle, which we call language local reasoning. And the idea, first, from an engineering point of view, is that we already have existing formalization, semantics, and problem logics for individual languages, say OCaml and C, maybe perhaps in ARIS. So we'd like to just reuse those as much as possible. But it's not just about reuse. From a conceptual perspective, if you're writing code in one language, say you are implementing OpenSSL in C, you just want to focus on doing that. You don't want to care about all the other languages that might eventually get linked into your code. You just want to focus on writing a correct OpenSSL implementation, which is already quite hard. So, and on the other side, if you're in OCaml and you call into this OpenSSL library, you don't care about the fact that some of it is implemented in C. You just care about the fact that it encrypts stuff. And it's really the job of the glue code in the middle to make sure that this reasoning actually works, to make sure that we can link these 2 languages in a way that we can later forget that we are talking with a different language on each side. And so this reasoning as if we are mostly in a single language, we call this language locality. And we believe it's quite important that our framework supports language local reasoning. So in Melocoton, we do use ARIS, and we do follow the ARIS methodology broadly, but where we build the problem logic on top of semantics defined in Coq, but we adapt it a little bit. First, to account for all the weird stuff that is happening in the glue code, we define operational semantics and the problem logic specifically for the glue code, and all of that is new. But we also want the language local reasoning part, and for that, we take existing formalizations for like mini OCaml and mini C that already existed in the ARIS world. We tweak them a little bit, and we embed them into our combined semantics and problem logics. And the idea is that at any point, then, when we are verifying a multi-language program, if we are in a part of the code which is in a single language, then we can simply drop down and use the normal problem logic for this part of the code, and reason as if you were in a single language. All of that is verified in Coq and in ARIS. And so this is the general idea of how we combine language interaction and language locality. And of course, there is quite a bit of tension between the two that we'll need to resolve. And so in the rest of the talk, I want to give 2 key ideas of how we make this work. First, I'll explain how we do this language local reasoning embedding of the existing languages and formalizations. And then I will give a second key idea of how we define language interaction. And then I will give you a brief tour of the structure of the Coq formalization. Very good. So the first key idea is that we take existing languages and program logics, and that by themselves assume that they just work on their own, and we equip that with a new minimal tweak, which is we equip them with the ability to make external calls to the outside. And at this point, from the point of view of each language, we'll just assume that the outside is always going to answer the call and give us the correct answer. All right, so this is a sort of minimal extension for now. An example of external call that we have seen in the OCaml part of the program is the call to href. Okay, href is not part of the OCaml program. It's just something that is part of the outside. Now, remember the arrays methodology. To give meaning to this new construction, we need to do two things. First, define its operational semantics, and then define how we reason about it in the program logic. So we do these with these two steps, and for the first one, we do something maybe slightly unusual, which is to say that this actually does not have a semantics from if we just look at this problem. Okay, but so we sort of defer the problem for later. But then in the problem logic, we still want to be able to reason about this problem in isolation. We want to prove something about this problem, that it is correct, maybe. And we want to reason at this point as if the href call was going to work and do what we expect. So in the problem logic, we're going to assume a specification for the call. More specifically, we're going to assume that it has the following specification. So this is in separation logic, so it's a hot triple with a pre and post condition, and the pre and post condition use points to, which describes the ownership of the OCaml reference. And so we will assume that href requires ownership of the reference thing that it contains an integer, and will return ownership of the reference having updated the integer inside. We don't really care about specifying the hashing, it's just another integer. And then if we just assume this specification for href, we can just now use the normal OCaml program logic to verify the rest of the problem. Great. Formally speaking, so what we do is that we take the standard separation logic triples that we have in separation logic to express specifications, and we now in Melocoton update those to have an extra parameter, which we call an interface, which we write psi here, and the interface basically just tells us what specification we assumed for the external calls of the program being verified, E. For completeness, the type in Coq here of this interface is as follows. It's an arrays predicate, which takes the name of the function for the external call being called, the list of arguments, the post condition that we want after, and it tells us the precondition that we have to satisfy in order to be able to make the call. If that sounds a bit mind-bending, that's all right, it is. The important part here is that this is a very general type, which allows us to put arbitrary arrays predicates here to describe the specification of the call. And this is actually a powerful principle that we are going to use to reason about the glue code. What we are going to do there is that we are going to say, I'm just going to verify this glue code using the normal program logic for C, and I will treat all the calls to FFI operations as external calls. Now, these operations of the FFI, so they are not C functions, and they do not behave as C functions, right? They do not operate on the state of the C program, they operate on the state of the ML program, which is in the outside. But that's fine, because what we can do is that we will assume specifications for these FFI operations that are described in terms of new assertions that are specific for the FFI. So whenever we want to reason about a glue code program, we'll just use the C program logic and assume a specific interface psi FFI which gives us specifications for all the FFI operations. And these specifications now are written in terms of this new block points to predicate, which I will talk a bit about later, but basically describe the glue code view of the OCaml data. And so, for example, a store field which writes into a block takes ownership of a block points to and returns ownership of an updated block points to, and we have other specs for all the other primitives. And by assuming this interface, now we can use the normal C program logic to verify the rest of the code and prove that CamL href has a specification where it takes, for the reference, a block points to in the precondition and produces an updated block points to. Very good. So let's sum up what we have so far. And so this is the code of our complete example. And actually what I've showed is that by simply reusing this single language program logics with minimal tweaks, we can verify all of the code. Excellent. But of course, we have verified all of the code by assuming in isolation that each part of the code assumes that the outside does the correct stuff. So the proofs and the languages are not connected yet. But what the cool part here is that actually we could still go over all of the code and prove some stuff. So now what's left to do is to actually connect all of the proofs and show that everything fits together. And the key idea is how we do this. The second key idea is how we do this. All right, so to zoom in a little bit, what we have is that we have assumed on the OCaml side that href follows this OCaml specification, and we have proved on the C side that CamL href has this other specification. But now in the code, when we call href, this is just going to call CamL href. So the two are not really connected at that point yet. They are more or less the same function, but we have two different specifications that have two different logical views about the same piece of state, which is this OCaml reference. So what's going on here? Let's back up a little bit and just look at what's happening in the code. So more broadly, the question here is, how is OCaml data accessed from the C glue code? And the answer is that C glue code can completely access the OCaml heap. So what here, they are really operating over shared memory. The glue code is just going to read into the OCaml heap, but is going to access this OCaml heap using a different memory representation than what is used by the OCaml code. It's going to use this lower level block representation of the ML values in terms of blocks and integers. So a bit more precisely, this is a PL talk, so we have to have a nice notation. Tilde ML, and we write tilde ML to say that a high level representation of an OCaml value is related to a lower level block representation as used in the glue code. For integers and booleans, these are just represented as integers. True and false become 0 and 1. Now, if we have more structured values, such as arrays and reference on the high-level OCaml side, these are just going to be represented as blocks. And a reference is going to be a block of size 1, an array a block of the same length as the array. And the same holds also for immutable data. So if we have a pair, it's also just going to become a block of size 2. And lists become linked lists in memory of these blocks. So on an example, if in OCaml code we create a reference on some nested pairs, the high-level view of the OCaml program in this normal semantics would be that we just create a location in the heap that holds the structured pair, which is just a structured value. But now, the glue code view of this data is that actually we have allocated 3 blocks, 1 block for the reference, but also 2 blocks for the pairs. And these are really heap allocated in this heap of blocks. So remember the Aris methodology. We need to define some operational semantics for that. And so on one hand, remember that we embed the existing operational semantics for ML. So we'll have a high-level heap that you would get from any standard operational semantics, which you write sigma here, which corresponds to the high-level view of the OCaml heap. But then when defining the operational semantics for the glue code that we need to define, it's much more convenient to reason in terms of a heap of blocks, according to this block-level representation that we have seen. So now we have these two heaps that represent the same data. So we need to sort of keep them in sync. And actually what we are going to do is that we are never going to have the two heaps at the same time, but switch between the two. And we are going to switch between the two whenever we are at a language barrier, which means that if we are running ML code according to the standard ML semantics, then we'll use the standard heap of this ML semantics. And then at some point, we'll make an external call. And boom, we are going to take all the high-level heap and translate it into this block-level heap. Then we run in the glue code, which operates on this block heap. And the glue code eventually returns. And at that point, the semantics will just take all this block heap and turn it back into an ML heap. Excellent. So to unfold this a little bit more, if we now consider the whole state of a multi-language program mixing OCaml and C, its entire state, I've omitted some administrative parts, but conceptually its entire state is going to be a pair of an OCaml heap and a C heap for the C data, for the C part of the program. And say we start by running ML code, this is going to update the ML heap, make an external call at some point, and then the glue code semantics kick in and turn our ML heap into a block heap. Then we run some C code, which might update the C heap. The C code might eventually call an FFI operation. Then the glue code semantics implement this operation and modify the block heap. And then this returns eventually and turns all the block heap into an ML heap back. All right. So to define the semantics of the interaction between these two languages, the operational semantics, this works. This is what we do. But now we need to define the program logic side of this. And here, it is a bit more tricky to make something that actually works and is nice to use. So for now, let's try something naive and see why it doesn't work. And we'll take it from there. So we are doing some separation logic, so we'll have our points-tos. Points-to is how we reason locally about the state. So a single points-to describes the contents of a single location in a heap, and then we have a bunch of points-tos that together describe the contents of the whole heap. And we have these two heaps, so we have two kind of points-tos, one for each. But then the idea, the issue, as I've just showed, is that we never have these two heaps. We just switch between one and the other. So when we go from ML to C, the ML heap disappears. So what should happen to these ML points-tos? One simple idea would be to just do the same. We'll just take all the points-tos and turn them back into block points-tos. And whenever we go back, we do the same. We take all the block points-tos and turn them all into ML points-tos. All right? So this means that the rule for the reasoning rule in separation logic for an external call would look like this. If you want to call into a function from ML, call a C function from ML, as a precondition, you would have to provide all the ML points-tos. You would get back all the block points-tos in return, and the reverse operation at the end. All right. As some of you might have guessed, this is a very bad rule. It's extremely bad. It's very non-local, non-modular. It doesn't really work. Why? Because in separation logic, we also have this rule, which is emblematic of separation logic, called the frame rule. And the frame rule is very good. We like the frame rule. It says that if we can verify a program E with pre and post condition P and Q, then all of the other resources we have not talked about are not modified. So we only need to talk in the pre and post condition about the stuff that we need. That's very nice. So if we have some other stuff R, we can just put R in pre and post, and it's completely preserved. Excellent. But now if we specify the frame rule with the call a C function operation, and then R with a random ML points-to, these rules mean that we can just forget about ML points 2 that we do not use. And now, this is incompatible with the other rule that tells us that you have to give all the ML points 2s in the world in order to make a call. So these rules are incompatible. And at a high level, what's happening here is that, on one hand, the semantics are defined by operating globally in the state, which is fine for operator semantics. But in the program logic, we want nicer local reasoning rules. So we cannot just do the same in the two layers. So the approach that works, the better approach, is to somehow make it so that OCaml points 2s remain valid when switching to the C code. So that means that we will have this cloud of ML points 2s, and then we call to some C code, and they are still there. All right. But maybe now the glue code is interested in accessing some of these points 2s, maybe some location L1 in the ML heap, but it cannot directly operate on it. It operates on its block level representation. So what we'd like to do is to turn this ML points 2 into a block points 2. Maybe we need another one. So we just turn another one into a block representation, operate on them, and then when we're done, we'll turn them back into ML points 2s, back into the code of ML points 2s. All right. And this means that overall, we have proved for a C function that it has a specification that can be expressed in terms of just ML resources, which is very nice because it means that now it should be safe to use from ML code, which is exactly what we wanted. So formally speaking, we justify this reasoning by providing these two view reconciliation rules that allows us to convert on demand between these two views of memory. The first rule tells us that you can take an ML points 2 and turn it into a corresponding block points 2 with related contents according to tilde.ml, if you remember tilde.ml, and related addresses. And the other rule tells us that you can go in the other direction, take a block points 2 with some contents that are related to some high-level contents and turn it into a ML points 2. So these are very nice rules because you can just use them whenever it's convenient in your proof. So how do we justify that these rules are correct? Good question. So the issue again is that whenever you're running ML code and you make an external code, the ML heap disappears. So what do we do here? What we do is that we'll have some extra ghost state, right, as you do in arrays. And we just have some extra ghost heap of the ML, an extra ghost ML heap that backs all the ML points 2 so that they are still tracked by the system. But then this ghost heap cannot be completely arbitrary. It sort of still needs to stay in sync with the block heap that is now here in the operational semantics. And defining this correspondence is subtle and really the crux of capturing the right reasoning principles for the FFI because it needs to be not too tight so as to allow weird low-level hackery that the FFI needs to do sometimes, but also not to lose so that we still have the view reconciliation rules. And I'll spare you the details. All right, so that's the idea. But now the good news is that we can finish the proof for href. So on the ML side, we assume this. Now we can use the proper rule for external calls, which is much nicer now and looks like this. It says that if you're in ML at the bottom and you want to reason about an external call to a C function f, passing it an ML value x as an argument with pre and post condition p and q, then you can just reason about the call in C about the function f with a different C value as an argument necessarily. But now this C value v, you can just assume that it is related in terms of tilde.ml to the ML argument x. And the precondition is the same. You just get to keep your precondition. And in the post condition, you just have to prove that you can return a C value which is related to something that satisfies the post condition. So basically on this example, that means that in the precondition, you can still have your ML points to ownership, and you have to give it back in the post condition. and the argument and return value are related to the C values that you actually receive. In the post condition, you have to return unit, which is related to value unit, all right? But now we want to operate on this reference in terms of these FFI operations, so we need to turn it into a block points to using view reconciliation rule number 1. We do our stuff, and then at the end, we need to turn it back, so we use view reconciliation rule number 2 to go from block points to an ML points to. And having done these 2 steps at the boundary, we are done because we have shown previously that the rest of the code works as we expect on these block points to. So the proof is done. Very good. And I could stop here, but we're at CoqPL, and I have not shown so far any line of Coq syntax, so this would not do. So let me do now a brief overview, a tour of the structure of the Coq formalization. And the Coq formalization is structured around this notion of language. If you're familiar with the Iris language interface, it's not too different. It just adds stuff for external calls. And so a language defines, so it's parameterized by a type of values, and it defines some operational semantics for the language with a type of expressions, state, and then a stepping relation between pairs of expression and states. All right? But now we have the stuff about external calls, so we want to first define that if we have a program, other people, the outside, can call into this program, and the program is going to be a collection of top-level functions. So we have a type for a top-level function, and a function that tells us if you call a top-level function and pass it a list of values, then you get this computation that you can run. And symmetrically, if you are running a program in this language, this program can make some external calls. So we have something to identify that a given expression is actually currently making an external call with a function name and some arguments in some evaluation context. And that's basically it. And yeah, so lastly, then we say that a program of a given language is just a collection of top-level functions with top-level function names. And you can think about this as a program, sort of a program module, or maybe the language level equivalent of a .o file is just a piece of code that you can call into and that can also call some other external piece of code. So yeah, so now the question is, can we do linking about these languages and programs? So can we do the equivalent of LD linking two .o files together and obtaining an executable? But we want to do this then at the language level for these language interfaces. So maybe we will take two languages which have a common type of value, at least. And then can we have two programs? Maybe a program P1, which implements function F1 calling to an external function F2. And then a program P2 with defining a function F2 that calls an external function F1. These belong to two languages, so there are some ... here, but the code could be different. Then what we would like to do, what would be very nice, is to link these two programs together into something that implements both F1 and F2 and makes no remaining external calls. So we want to dispatch the calls inside the program so that everything is resolved. And so what this means is that we want some link prog operator that gives us a closed program of this of some language. But this language cannot be L1 or L2 because now we are mixing code of two different languages. So what we do is we do exactly this. We define a new language which corresponds to the linking of two other existing languages. So link-lang is a language for linking of L1 and L2, and then we have this link prog operator, which takes two programs of language L1 and language L2, and gives us a program of this link language. And intuitively, the idea is that now execution of a link prog is just going to take these two underlying programs and run them one and the other, and just dispatch the calls between the two. So one is making an external call implemented by the other, is going to run the code of the other, and so on. So a bit more formally, an expression of this linked language is going to be the currently running expression on the left, which is either going to be an expression of language L1 or language L2. And this runs under a stack of evaluation contexts, which interleave context of language L1 and context of language L2. And whenever this expression makes an external call, it's going to take off the context, put it on the stack, resolve the call by running the other function from the other program, implementing the call, and continue. Okay. Note that I've cheated a little bit and that I haven't talked about how we can share state between the two languages. This doesn't work as is because the languages have different type of states, but there are some extra stuff so that they can communicate with shared memory. Very good. So, and as you might expect, we have taken our formalizations of mini-C and mini-ML, and they are inhabitants of this language interface. So now can we just link them together? Well, no. This doesn't work because they just operate on different values. They don't really know how to talk to each other at this point. So remember that our link lang could link languages with the same type of values and actually sort of compatible states. Here, these are not compatible at the moment. And indeed, we have just not defined the FFI semantics, how we can bridge between two languages. So we need to do that. And this is done by defining yet another language, which we call wraplang. And wraplang here is defined, so it's defined as it as its own language, but essentially it embeds MLlang. So it embeds the semantics of running ML code, and it adds new semantics for the FFI on top of it. And so this results in a language which inside can run ML code, but is an inhabitant of language with C values. So you can talk to it by calling the C calling convention, and inside it is just going to run ML code. And it's going to use the FFI semantics to translate at the boundary. And indeed, we have this wrapprog function that can take a random ML program and turn it into a program of this wraplang language. And intuitively, if you do this, then the program wrapprog E is going to emit the same external calls as E, but then translate it at the boundary to use and receive C values. And then, if you are from the outside, you can also call into wrapprog E, and this will implement all the FFI operations. So wrapprog E gives the semantics to the runtime. It equips E with all the OCaml runtime operations, and it also provides a main function that you can call at the top level to just run E. And now that we have this, well, we can combine this stuff to get our full semantics for the entire system, which we call combined lang, which is the linking of the wraplang and the C language. And we have a combined prog operator, which allows you to take a ML program, a C program, and link them together with the adequate wrapping. All right. And so this is how we structure the system. This was just about semantics. So now we need some reasoning principle at the level of the problem logic to reason about those. And very shortly, these are simply structured around a notion of program triple, which you write like this. And this is basically the equivalent of for triple, but at the level of entire program modules. And it is read as follows. Assuming interface psi, we have proved that program P correctly implements the interface pi. And if you have concrete programs at hand, you can prove this by stepping through the code and using the rules of the program logic. Essentially, you just have to prove a triple for each top-level function of the program. But now the very nice thing is that we can use this to express the correctness of our linking and wrapping operators. And this gives rise to very nice statements, such as correctness of linking, where if you take a program P1, which assumes pi and implement psi, from P2 that assume psi and implement pi, so they each assume and implement the stuff that the other implements and assumes. Then you can link them together, and you obtain a problem that assumes nothing and implements the two. As an administrative side condition, the problem have to contain different functions. Otherwise, there would be some ambiguity. And then for wrapping, this is slightly more hairy, but essentially, if you have an ML expression E that you prove is safe, it's just going to be called by the main function. So in itself, we just have a trivial specification for it, and assumes some interface psi for the C function that is going to call. Then wrapping this expression assumes a wrapped version of psi, which I have not defined here, but essentially just adds this tilde ML relation for inputs and outputs. And this now implements all the primitives of the FFI and this main function that we can call. And so the idea is that if you have an example such as the href example before, you will use the rule of the program logic to prove program triples for concrete parts of the program, use this two lemma to put them together, and you will obtain a statement that tells you that you have a closed program P, a multi-language program, that assumes nothing and implements a top-level main function. And if you do this, then you can apply the adequacy theorem of Melocoton, which tells you that then in the operational semantics, this program is safe to run, which is the criteria that we use to say that we have proved that all is good. And yeah, as usual, this adequacy theorem effectively extracts correctness in the logic into safety in the operational semantics. That doesn't depend on any array stuff. Okay, so let me conclude. Let me conclude with what I've told you so far, the top-level key ideas, what is in Melocoton but I've not told you about, and some plans for the future. So what I've shown is that we give in Melocoton a sort of general recipe for merging two languages. First, you take the languages on each side and abstract over the other side using these external calls and interfaces. Then you need to formalize the semantics of the FFI to define how the languages are going to interact. And in order to bridge memory models at the program logic level, you can use this view reconciliation technique. Also in Melocoton, but that I have not shown, first, a sort of technical point, we use angelic non-determinism to define the FFI semantics for the step where you go from a block heap to a high-level heap, because a low-level value does not have a unique representation as a high-level value. So to avoid making a choice, here we use angelic non-determinism. And this in turn requires the use of transparent arrays to have an adequacy statement that works. But yeah. Then we formalize more various aspects of the OCaml FFI. If you are an OCaml programmer, you might have been sort of confused why I haven't talked about all the weird stuff with the GC and the root and so on. We do formalize it. I've just not talked about it. But once we have this setup put in place, it's not that hard to define. We also formalize callbacks where you can invoke an OCaml closure from C code and some limited form of custom blocks. And then something which I think is really nice is that we can leverage the very standard technique in the Iris world for building a semantic typing logical relation for ML types. And we just adapt this a little bit, but this is very easy, for external calls, which are annotated with these ML types, so that now we have verification conditions to say that maybe we have implemented some weird C plus OCaml plus FFI code which use some unsafe stuff, but now we can prove that it obeys some type-safe interface as an OCaml type. And now we can stop proving stuff, because we know automatically that any type-safe OCaml code, OCaml context, that uses this library is going to be safe, because this library implements a type-safe interface. So this is also very nice. It's something that we get almost for free by just using Iris. All right, so some ideas for future work planned. And ongoing is to extend this model with remaining features of the FFI that we have not modeled yet. And we have the beginnings of a static analysis tool for FFI glue code. More ideas would be to maybe go and model the multi-core OCaml FFI, if someone is courageous. Turn into maybe try various verification or bug finding or runtime analysis techniques for FFI code, maybe based on the operational semantics or problem logic of Melocoton. Maybe a different approach is to just give up on trying to verify C code and instead build a DSL for writing this FFI glue code, maybe with built-in verification conditions. Or just try to extract reusable bits of this formalization into Iris libraries that other people could use for multi-language problem logic building. I don't know. If any of these sounds interesting, I'm happy to talk about it. And with that, thank you for your attention.
Thanks. Are there any questions? Please go ahead. Armaël, do you want to choose the questions? Or?
Oh, yeah, go ahead.
Okay.
Yeah.
Thank you. You said that for OCaml, the operational semantics of an external code has no semantics, so it gets stuck. Maybe I missed it, but I don't remember you saying what is the operational semantic on the C side.
Right. So yeah, good question. So if we consider just the semantics of one language, so either the OCaml side or the C side, external codes have no meaning, but eventually they are given meaning by these linking and wrapping operators. So in the end, if you just look at the semantics of one language, then external codes do not do anything. But when you combine them, then you consider the semantics of the language plus the linking operator, plus the wrapping operator, and now everything becomes connected with this additional translation done by the wrapping wrapping semantics.
Okay, thank you.
Jean, well, okay. Yeah.
I have a question about that val int in the program that you showed.
Yeah.
I assume on the C side, hash pointer returns a 32-bit integer, but OCaml ints are 31 bits. So what happens with that 1 bit from C?
Let's see. That's a good question. I guess that wouldn't work in that case, yeah. Yes, I am papering over any integer size issue here.
Right.
So the integers that you get from OCaml becomes a 31-bit integer in C.
Right, that one that works.
But then you hash it, and then you get maybe a larger integer.
Right.
And then you are in trouble. Yeah. So the person writing this glue code would have to do some extra work.
Okay.
Yeah. Because I think like val int is going to drop the extra bit.
But could you possibly change the spec of val int so that it says the thing you pass it should be less than 2 to the 31?
Yeah, that should be in the spec of val int. Yeah.
All right.
Yeah.
Cool, thanks.
So I have a couple of questions. So the way you define sort of individual languages, it seems to be sort of very symmetric. There's no language that is sort of better than the others. But then when you showed how you linked it in the specific case of OCaml and C, it seemed like C had a sort of privileged status. Mm-hmm. Is that a general thing, or is that just specifically in this context it was helpful?
Yeah, that's a very good observation. And so, yeah, indeed, as you say, like this picture looks very symmetrical. That's a lie. Yeah, indeed, there is an asymmetry here in that the way the FFI works, at least for OCaml, like in the code, is that linking is done with LD, like the system linkers, and it's a C linking model, as I understand it. So, and also like, so C does not have to know about OCaml. C just produces a C program that gets links into what it's going to assume another C program. On the OCaml side, OCaml has, if you link just OCaml program together, OCaml has its own linking language. And so the OCaml FFI semantics has to know about C so that it can produce something that obeys the C calling convention, the C linking model. So there is really, so this is where the asymmetry comes from, is that the C language also shares a linking model with the platform linker that you use to link these languages together. So as I understand it, this is where the asymmetry comes from. If you were with different languages and different models of linking, things might be different. If you know of example of that, I'm interested. Does that answer the question?
I have a second question. I hope I'm not stepping on anyone's
Go ahead.
feet. That is kind of related. So at some point you showed this operational semantics that had sort of two heaps, one on the left for ML and one on the right for C. And I was wondering, are they sort of, is there any permeability? Can you move things from the left heap to the right heap and the other way around?
Yeah, so as is written here, no. In practice, yes, a little bit, and probably more when we implement more aspects of the FFI. So what would happen here is that what happens today in the semantics that I have not written here is that whenever you go from the ML heap, so when you do this step, the ML heap is going to be translated into a block heap, but also an extra piece of C heap that you merge into the C memory. This is used for the root right now. And when you go the reverse direction, you take out this piece of the C heap and you use it to produce the ML heap. So right now we have this limited use case, but in the actual OCaml FFI, what you can do is you can have, say, byte arrays, OCaml byte arrays, and pass those to C, and then C can do mem copies in there. And then whenever C returns, then you get updated byte contents as an OCaml value. So we do not model these right now, but it would use the same principle where you have a piece of C heap that can be shared and given to C and then taken back. If?
So the whole point of this formal verification is to catch bugs.
Yes.
And when we looked at this example with integers, there's a possibility of bug. Where is the catching process happening? At what point is there a leap of faith in the description of the whole framework? Where is the mistake? Where can we leave a mistake?
Why did I not catch the valInt bug? Yes. The leap of faith is that we define by hand some operational semantics, which we say this is the operational semantics of OCaml and its FFI. So that's sort of ground truth. That's what we define and take as ground truth, and we build the problem logic on top of that. So the problem logic is proved sound on top of our operational semantics, but the operational semantics we just thought very hard and defined.
Okay.
Yeah. So that's the leap of faith, I would say. But I mean, it's the same leap of, in principle, it's the same leap of faith that you do when you take any iris formalization of, I don't know, like mini-ML, and you start by writing some semantics for mini-ML, and these semantics are just assumed.
The same leap of faith when we say comcert C is C.
Exactly. Yes.
Yeah, it's a bug in OCaml, right? They didn't verify that valInt preserves all 32 bits according to the spec that we
Yeah, but this is knowledge you have, so this is something we can encode in the description.
Hi, thanks for the talk. And related to the two last questions, so would it be possible to verify the FFI implementations with that framework or another one?
So, I mean, I guess this is a step in that direction, but I don't know how to do it. The way I see it, it amounts to a compiler proof. In some sense, the FFI is the way I see it. The FFI implementation is the output of the OCaml compiler when it takes source OCaml code, which does not know about the GC, has this high-level semantics, and produces low-level code that can now materialize the runtime part that also include the FFI stuff. So I would say that this source-level FFI semantics would have to somehow connect with this compiler proof, but I really don't know how to do it.
Oh, okay. So the inval, the store field, and so on are not like C functions that the compiler calls?
They are mostly written in C. I do see that as an implementation detail because they are written in C, but also the runtime is implemented in C with some bits of assembly. So it's not like there is a clean barrier of abstraction between the code produced by the OCaml compiler and the runtime. Like the code produced by the OCaml compiler outputs some symbols that the runtime hooks into and so on. Mm-hmm. So yeah. So the way I see it is really, okay, this is just a big stuff that is produced by the compiler, and maybe some part is in practice implemented in C once and for all.
Okay.
But yeah, maybe I'm wrong, but that's how I see it.
Yeah, and just one quick question. Mm-hmm. Regarding the two heaps, is it possible that somehow the C heap is not empty when the...
What, you mean when the program starts? Or the C heap can if you do malloc in C, this will create some stuff.
Yeah, but like for example, in your operational semantics, you start in ML, blah blah blah, and then you do the external call. So you have to translate the ML heap into block heap. Mm-hmm. At that point, can the C heap be non-empty before doing the external call or not?
So if you haven't run any C code before, typically it will be empty.
Okay, but if you had done other...
If you have run other C code before, then this might have malloc stuff that you might want to reuse again, and then this is in the C heap.
Okay, so that's why you had two heaps.
Yeah.
Okay. Yeah. Okay, thanks.
Thank you.